Everybody. Today we are discussing the next topic in supramolecular chemistry, that is the supramolecular photochemistry. Supramolecular photochemistry means when a molecular chromophore is irradiated with an electromagnetic radiation of the wavelength corresponding to the energy required to promote an electron. The electron is excited into any one of the higher energy state. So it is represented by S1, S2 and T1, T2 depending upon the state. And in the excited state, it can liberate its energy in the form of three types. First one, it can either be dissipated as heat. This is written by the dotted line. I have shown by violet dotted line, or emitted radioactivity. That means it may be fluorescence or phosphorescence. That I shown by the green is the fluorescence, that is transition from the singlets to S0, or phosphorescence, that means the transition from triplet state to ground state. T1 to S0 is the phosphorescence and fluorescence is S1 to S0. Or the third this energy, the energy which is in the excited state can be used for carry out the chemical reduction or chemical reaction. These are the two categories while we are doing the photochemical reaction. So this property of the supramolecular chemistry can be used in the different application. First is the process of re-emission of the radiation by the luminescence is used in sensing and signaling application. Or the chemical reaction, that is the third category, is used in the molecular switches and photocatalysis. So there are three processes are involved in the supramolecular chemistry. First is the binding of substrate and receptors. Second is the mediating a photochemical process such as energy, electron or photon transfer. And the third one is the restoration of the initial state for new cycle or by a chemical reaction. These three processes are represented in the form of a diagram. First step is the receptor and substrate combine together or bind together, and we will get a supramolecular, which is represented by RS. R is the receptor and S is the substrate. Then after the combination, the molecule is illuminated by the radiation. So this supramolecular is undergo excitation. The excitation may be R, excited molecule may be R or S. So if it is an R, we can get R star S, or if it is an S, it is R S star. After the excitation, it may undergo the two type of transfer, that is energy transfer or electron or hole transfer. If it is undergo the electron transfer, the R transfer its energy to S, or excited S star transfer its energy to R. After this transferring, this energy is converted in the form of radiation, or it may emit the radiation. After that, it come back to the initial state. Or in the excited level, it can transfer the electron. So we will get R plus S minus or R minus S plus. After the transfer, it is they will recombine, or sometime it may undergo chemical reaction. After that, it come back to its initial state. These are the three steps which are involved in supramolecular chemistry. Next is the light conversion and energy transfer devices. So the important application of the supramolecular photochemistry, first application is the light conversion and energy transfer devices. So in which an absorption, energy transfer, emission absorption or energy transfer or emission process is occurs in which light absorption by a receptor molecule is followed by intramolecular energy transfer to a bind substrate which then emit the radiation. So an optimum device can be used to measure this light absorber or light emission or the degree of the coupling of this material between them. But instead of that, we are using the combination of the coupled absorber or an emitter, coupled absorber and an emitter produces light conversion devices with optimal properties such as maximum light collection or emission at the desired wavelength. An example for this device is the europium-3 or terbium-3 cryptates of macro bicyclic ligand, that is bipyridine. That is the molecule macrocyclic ligand in which UV light is absorbed by this bipyridine group, which is transferred to the lanthanoid cation, which is bind in the molecular cavity and released in the form of the visible lanthanoid emission. This is the example. The first one is the tris bipyridine cryptate, in which europium in the 3+ oxidation state is encapsulated. After that, energy is transferred, the energy is absorbed and the energy is transferred to EU3+. After that, it is emit energy. So in this molecule, EU3 or terbium 3+ complex display a bright luminescence in aqueous solution, whereas the free ion do not emit under the same condition. That is the difference. So we can easily dictate this molecule. So next device is the photo-induced electron transfer in photoactive devices, in which there are 3 components. First one is photosensitizer, which is linked to electron donor, that is the second component, and also linked to electron acceptor, that is the third component, and possessing suitable redox property, in which in this group an excite property, and in this group the photosensitizer is excited to the higher energy level by after absorbing the radiation, and in the excited state it will transfer its energy from the donor, and after that donor it transfer its energy to acceptor, yielding a charge separated triad, that is D plus PS A minus, that is shown in the last figure. The charge separated state that is shown. So this is the photo-induced electron transfer in photoactive devices. An example for this is the macrocyclic core receptors containing both the photosensitive porphyrin group and a binding site for silver ion as a receptor center, and this result in quenching of the singlet excited state of zinc porphyrin centers by an efficient intramolecular electron transfer and leading to a charge separation and generating a porphyrin cation of long lifetime. So here the zinc porphyrin center will absorb the energy and transfer to Ag+, so we can retain or we can increase the lifetime of the Ag+ ion.